in this video, I'm going to introduce gases, and so just a couple of characteristics of gases that you should have covered in first year chemistry, or just kind of common sense as well. It's the fact that gases, they expand to fill the volume of a container. That's one characteristic. Another one is that they're highly compressible because there's a ton of space in between gas molecules. And since they're so spread apart, they actually act independently of each other. So they're not attracted to each other, and instead they kind of coexist. And we'll look at how that influences our mathematics a little bit later on when we're working with gas laws. Really quickly, to talk about pressure, pressure is the force that's exerted on a given area. So for example, if I'm stepped on by someone with wedge shoes versus stilettos, the amount of pressure my foot experiences, the force is the same, but the amount of pressure is much larger for the stiletto heel, and therefore it hurts a lot more because the area over which the force is exerted is much smaller. So that's why getting stepped on with stiletto heels hurts so badly. And the last thing to talk about is atmospheric pressure. Now, atmospheric pressure is the force exerted by the Earth's atmosphere. So right now, the atmosphere is actually pushing down on us. The gases in the atmosphere are pushing down on us, and we're experiencing that atmospheric pressure. Now, the barometer is one tool that's used to measure atmospheric pressure, and what it is, it consists of a tube that's filled with mercury, and the atmospheric pressure pushes down on that open bath of mercury that you see right there, which would then cause the mercury in the tube to rise up the higher the atmospheric pressure. And so one unit, I'm going to talk about units of pressure in just 1 second, but 1 unit of pressure is a millimeter of mercury, and the standard for that is 760 millimeters of mercury, because when you're at normal standard pressure, the amount of atmospheric pressure causes the mercury to rise up 760 millimeters of mercury.
So one of the first things that you need to learn as far as gases are concerned is the units for pressure. Now, the units for pressure include millimeters of mercury, atmospheres, and then also kilopascals. So the relationship is that there are 760 millimeters of mercury in 1 atmosphere and in 101.3 kilopascals. So let's work on converting from millimeters of mercury into atmosphere. So I have 1,277 millimeters of mercury. That's my given. So I'm going to get out of millimeters of mercury by putting that unit on bottom. And then I'm going to get into atmospheres by putting that up top. Now all I have to do is put the relationship. So for every 1 atmosphere, there are 760 millimeters of mercury. And so I'm going to take 1,277 divide by 760, and what I get, I want 4 sig figs, so I get 1.680 atmospheres. Okay, so I've converted from 1 unit of pressure, millimeters of mercury, into another unit of pressure, atmospheres. So in this class, we're going to be working with 5 different gas laws. Gas laws allow you to relate pressure, volume, and temperature. And so the best gas law, the gas law that encompasses all of your gas laws, is the combined gas law. It includes Boyle's law, Charles' law, Gay-Lussac's law. And so the formula for the combined gas law is P1 times V1 all over T1 equals P2 times V2 over T2. Now, you're going to be using this formula if you're changing pressure, volume, and temperature, all 3 of them. If you're only changing one of the variables, then you're going to use one of the other gas laws. Now, the only thing that you need to keep in mind as far as units are concerned, you need to make sure that they're the same on each side. So if the pressure is in atmospheres, it must be in atmospheres on the other side. But the 1 unit that you have to be in for your combined gas law, for Boyle's law, for Gay-Lussac's law, for Charles' law, for all of these, when you're dealing with temperature, the 1 unit that you have to be in is for temperature, and that is Kelvin. Okay, so let's do an example problem. So in this, a child has a toy balloon that has a volume of 1.80 liters. The temperature is 20 degrees Celsius, and the pressure is 1 atmosphere. So P1 would be 1.00 atmospheres. Okay, V1 would be your 1.80 liters. And then you need to take your temperature, which is 20 degrees Celsius, and get it into Kelvin by adding 273. So my temperature would be 293 Kelvin. Okay. Then After the balloon has risen, the pressure would decrease as you go higher up, and therefore it says that the new pressure is 0.667 atmospheres. I don't know the new volume, so I'm going to just plug that in as V2. And then the new temperature is negative 10 degrees Celsius, but I've got to convert that into Kelvin, so it's going to be 263 Kelvin. All right? So what you need to do to solve for V2, cross multiply. So you would take 1.00 times 1.80 times 263, and you'd set that equal to 293 times 0.667 times V2. Then divide both sides by the product of these two, and that will give you your V2. Now, you do not need to write all of that out. If you can plug that all into your calculator, that's ideal just to save time. And since you want 3 sig figs, I got 2.42 liters, and that's your answer. Okay, so that's a combined gas law in which I'm changing all 3 variables. What if I'm only changing 2 of them? So for example, for Boyle's law, it's simply P1V1 equals P2V2. So what I'm changing here is just pressure and volume. And as your pressure increases, the volume decreases. That's what this equation is showing you. And so there's an inverse relationship between pressure and volume. If you increase pressure, the volume is going to decrease. So let's look at this example. So here it tells me that my volume is 30 liters and my pressure is 103 kilopascals, so 103 times 30 liters. And I'm going to set that equal to the new pressure, which is 25 kilopascals. Well, based on the conversation we just had, you would expect the volume to increase. And when you actually do your math out, that's exactly what you find. The volume goes from being 30 liters to being 124 liters. So that is your answer. So Boyle's law states the relationship between pressure and volume, and specifically it says that they are inversely related. While Boyle's law talks about the relationship between pressure and volume, Charles's law talks about the relationship between volume and temperature. And so the formula for Charles' law is V1 over T1 equals V2 over T2. So notice this comes from your combined gas law, except we're keeping the pressure constant, so we ignore it. Just like for Boyle's law, we kept the temperature constant, and so we ignored temperature in that case. Keep in mind again that temperature must be in Kelvin. And notice this relationship is different from Boyle's law, and therefore volume and temperature are directly related. If you increase the temperature of a substance, its molecules are going to be moving much quicker. They're going to collide with the container and actually cause it, if it can, cause it to expand. So it's going to increase the volume. So higher temperature means larger volume. So here I start off with a volume of 4 liters. And the temperature is 24 degrees Celsius. So I'm going to add 273 to that, and I get 297. Okay. Well, I'm going to increase the temperature, so I'm going to see what happens to the volume. I'm going to assume that it is going to increase because they're directly related. So 58 is the temperature, but I need to add 273 to that, so that would be 331. And so when I'm going to cross multiply these and then set it equal to 297 times V2, divide both sides by 297, and what you should get for V2 is 4.46 liters. And that's your answer. The last gas law that we're going to talk about before the year starts is Gay-Lussac's law. So we already worked with Boyle's law, which was P1V1 equals P2V2. We worked with Charles' law, which was V1 over T1 equals V2 over T2. Now we need to relate pressure and temperature. So Gay-Lussac's law states that P1 over T1 equals P2 over T2. And notice this is just like Charles's law, so therefore pressure and temperature are directly related, which makes sense. If you increase the temperature of a substance, it's going to move more quickly, and therefore the molecules are going to collide with the container with more force and more frequency, therefore increasing the pressure. So this gives me the pressure and the temperature. So this is my first pressure. My first temperature I need to convert to Kelvin. And so that would be 300.9 Kelvin. And then my new pressure is 3.74. Well, since my pressure decreased, I know that my temperature must have decreased as well, but let's check it. You're going to multiply 12 by T2 and then 3.74 by 300.9. And so what you will end up getting for T2 once you divide by 12 on both sides is 93.8 Kelvin which is a decrease in temperature, which is what we expected to see.